General Relativity, Chapter 1, Section 5, the Divergence Theorem. Here's a very simple derivation of the Divergence Theorem. Now, here what you're doing is you're calculating a flux out of a region that's enclosed. I have a very simple case where I have an electric field that's pointing in the vertical direction, and we have a bottom value and a top value. And this integral means we want to take the vector perpendicular to the surface and integrate. Here we would just simply multiply, since that's constant. We would take this area and multiply by the magnitude of the vector there. So here I have the vector skimming the surface on the other sides here, just the bottom and the top is all you have to worry about. So at the top, the vector has the value you find at x, y, z plus delta z, and at the bottom it has the value when you put in for the function x, y, and z. The area is given by delta x and delta y here. So when we do the subtraction, since here we're going into the box and here we're going out of the box, we went out of the box minus in. That's our convention with the signs. So when we do that, we slap down a delta z and a delta z here that cancels so that we have a volume element. And then we can go to the next step and see that we have here a volume integral. The surface integral becomes a volume integral, and that is the divergence theorem. It's a very, very nice result. So here we're looking at a derivative, a partial derivative of the z component with respect to z, as we set up here. And in general, we would have the derivatives with respect to x and y in a similar fashion. So this is the divergence theorem. Here's a little homework problem for you to try it again with a little different approach with the deltas. And here we're going to do it in general. So we have a general case where we have curvilinear coordinates where things are curvy. So we have the scale factors, the h's, and the deltas. Here we're going to use u, v, and w for the three variables. And if we set this up in a similar fashion, the only thing we have that's different is we have the h factors here, like you think of like r, d phi for polar coordinates, or r sine theta, d theta. So we have those in there too. So when we look at the area, we have the h times the coordinate differential. And these are functions of the coordinates. So when we look at the top value, we have w plus delta w, and the bottom value is going to be with just a w. This is kind of like your z and z plus delta z, which we did earlier. So doing the similar idea where we have the flux going out at the top minus the flux going in, we get a very, very similar result. You should work this through. This takes some time to work it all out. And here we have a partial derivative with respect to w, like we did earlier with respect to z. And the difference here is that you have some h's that are in there with the vector field. So when we come down here in general, we're going to generalize this with the other components. We go ahead and replace the w with the third component. So you should work through this. These steps are not too complicated. You basically just have to write things out to get familiar with what's going on. Always best with theoretical physics to write things out. And this is our general result of the divergence of a vector in curvilinear coordinates. And for a homework assignment, for you to get really familiar with this, you use the h values for the Cartesian, cylindrical, and spherical cases and derive these three results. This is very powerful stuff and useful for you in all fields of engineering and physics.